Okay, here you can see the slide showing you the permanent magnet stepper motor. Okay, from now up to the end of this stepper motor discussion, I'm focusing the attention on the permanent magnet motors, okay, because they are most of the time the most employed stepper motors you can find in everyday applications. Okay, so let's focus on PM motors, and just to say overview something that you already know because we discussed it before Easter. Here there is the say very simplified schematic description of the operating principle of this kind of motors. In this situation, we have four stator poles, okay, that are indicated in this slide by this expansion. Okay, and then you have the rotor, which is a circularly shaped rotor, but in which you have embedded permanent magnet. In this case, you have two poles, okay, north and south pole in the rotor. Remember what I said, that in order to make possible the rotation in alpha p elementary step, you have to excite, in this case is a one phase on description, one phase at a time. Okay, for example, look at the first situation, which you have a current entering the node A, no current excites the B phase. Okay, the current flows in these, say, coils. Okay, the two poles, okay, vertical poles are, say, in series in terms of the coils. So the current entering the node A will exit the node A prime here, generating a south pole on the upper expansion and a north pole on the lower expansion. Okay, in that case, you have alignment of the rotor according to this magnetization. So the north pole of the rotor is, let's say, close to the south pole of the stator, etc. Then if you want to have alpha p 90 degree, then you have to de-energize the phase A and energize phase B, okay, putting a current entering node B, okay, and nexting B prime, having the magnetic poles as indicated in this figure part B, north on the left, south on the right, in order to generate the rotation alpha p 90 degree, etc., etc., etc. Remember that this kind of rotation is totally sensitive to the direction of the current flowing through the coils. Okay, for example, if you want to get from the B situation another 90-degree clockwise direction rotation, so you have to put from B to move from B to C, then you have again to energize phase A, but now the current will be reversed. Okay, the direction of the current is opposite to that you had in phase A. Okay, now the current is entering A prime, exiting A, so the direction is totally different. Okay, in order to generate south on the say bottom here, the lower expansion, north pole on the stator upper pole. Okay, so the direction of the current flowing in this winding is important. So I said before, and this is true for PM stepper motors as indicated here, that the phases, for example, the phase A, which has these two expansions, one and the other one is opposite, have the same coils. So the coils are in series. Okay, they have the same current flowing through them. So let's have a look to the way you can wire the phases. Okay, there are two basic mechanisms by which you can have this kind of wiring in the stator phases. Okay, for example, what I described up to now is what is called the bipolar configuration. Okay, in which, for example, look at these two winding in this picture. Okay, here you have 1 and 2 terminals and 3 and 4. For example, in this simple assumption, you can say that 1 and 2 are the same as the node A and A prime in my previous discussion, and 3 and 4 are similar to the node B and B prime. Okay, so the winding 1, 2 is the phase A. Okay, and the coil connected between the node 3 and 4 is that you have for the phase B in the previous example. Okay, this is exactly what I described before. You have two, say, windings. Okay, you have these coils, and then you can have bipolar current, so bidirectional current flowing through these nodes in order to excite the north and south pole for the stator expansion to get continuous rotation of the rotor. Okay, just say more detail on this bipolar configuration, sharing the white screen. Okay, here. And so let's start with the bipolar configuration. Bipolar configuration means that you have, for example, this kind of configuration. Let me call this A and A prime, just to make a, say, direct relationship with the operation principle I discussed you before. Okay, this node can be connected to, for example, a power supply. Let me call this V. Okay, this can be connected to, say, 0, and so as you can see, there is a current flowing in this direction. Okay, but this is not the only possibility. Okay, you can have A prime connected to a power supply. Let me call this again V, and A connected to, say, 0. And then in this case, you have this current flowing in the opposite direction. Okay, this is what we have in the picture, for example, number A of the slides. Let me just have number 17, slide 17. Okay, and this is what happens in the slide, in the part C of the figure in slide 17, discussed before. Okay, so we have two different ways of energizing the phases, and this bring to different configuration of the magnetic north and south poles. In order to drive this kind of bipolar configuration, which is the simplest one, and I showed in my previous discussion, we need a specific driver, which is the bidirectional driver. Okay, this bidirectional driver requires what is called a full bridge or an H bridge. Okay, they are the same. Sometimes you can find full bridge, sometimes H bridge. Okay, this is something that we can study later in this course. Okay, so later. So we see how to get this behavior that I simplified with this battery V and the short by using the full bridge or H bridge, but this is a topic that we discussed later on this course. There is another possibility, and it is fully exploited in stepper motor to drive the wiring of the phases, which is called the unipolar configuration. The unipolar configuration is made by, let's say, the winding, which is connected between node A and A prime. Of course, we have the same winding for BB prime, CC prime for each of the phases. Okay, so this is just the description for, say, a single phase. Okay, but you have to multiply it for the number of phases you have. But then in the between of these two of this winding, there is a third terminal here, which is a common terminal. And what happens? This common terminal is always connected to a power supply. For example, let me call this V. Okay, so this common terminal is always connected to this battery V. And then what happens to the these end terminals A and A prime? They can be left open, or they can be shorted to ground. Okay, so they can be driven in this way. So what happens, for example, when you have, for example, the terminal A, which is connected to ground. Okay, so here you have V. This is connected to ground. This is open. Okay. And so in this case, we have a current flowing here. When this switch is closed, connected to A prime will be left open. So the two switches act in a complementary way. Okay, they are not closed simultaneously at the same time. Okay, when the opposite happens, so it will be here, open A prime and shorted, open A and shorted A prime. Now the current flow in this sense here. So there is a current, okay, which always flow from the center common terminal to the ends, A and A prime, B, B prime, etc., but just in half of the winding, okay? So, for example, this first situation can be exploited for the case, let's say, bring it to the part A of slide 17, and this can be exploited for the phase C of the behavior you can find in the figure in slide 17. Okay, but in this way, you could always understand that the current flowing is from the center tap here to the terminals. So the current is always unipolar, means that you have no current flowing, for example, in this sense from A to the central terminal or A prime to the central terminal. This never happens. Okay, so the current flow in half of the winding in the series of the phase, but just in a unipolar fashion. This is the way, this is why this is called the unipolar configuration. There is the possibility to have, let's say, both switch left open, okay, but never the switch are closed at the same time. Okay, so there is another configuration, which is the third one, in which the both switch are left open. So let me draw this third possible configuration, which you have the V connected here and then open and open. In this case, both the phase, both the terminal A and the prime are left open, no current flows in the phase A, and so this is the case in which the phase A is not energized. Okay, so for example, this happens in the part B and D of the figure you can find in the slide 17. Okay, so when you energize another phase, for example, the phase B, you have no current flowing here. So 3 different possibilities that can be employed here. Okay, of course, in the bipolar configuration, okay, you can have this case. This case is I just depicted here, but then you have another case, which is the situation in which you have the, let's say here, one of the terminal which is left open. In this case, there is no current. Okay, and this is the case in which you don't have any, you do not energize the phase. In this case, the phase A. Okay, so this happens also in the bipolar configuration. So let's just use from now on this unipolar configuration. Let's see what kind of circuits we need for obtaining this behavior I show you in this simplified form. Okay, so permanent magnet stepper motors, which are unipolar configuration of the wiring for each phases. Okay, so let me just illustrate what happens in this case, sharing the, say, stepper motors slides, okay, here. And so let me see, just start from the bipolar, just to say finish this topic here. Okay, this is the bipolar configuration. I said this is something that we, in terms of the circuits we need to get this behavior, we will use the full bridge, something that we have to study later. But just as a principle of operation, it is quite simple, okay, because it's exactly what I explained to you in the previous slide number 17, which is this one, okay, here, this one. So just say this, an overview. This is the configuration. You can see there is the rotor here, which is the circular shaped rotor with 2 poles, north and south. And then you have the stator. There is these 2 big C here, okay, ferromagnetic material. Then you have winding, okay, here. Each winding is bipolar in the sense that you have just 2 terminals, A and the prime, B and B prime, exactly as indicated here. And then you have to consider what happens by putting, for example, the current in the phase A and not in the phase B. So let's start with the number 1. You put V here, okay, at the node A prime. You short the node A, and so a current flow with the direction of the yellow arrow here. And this makes possible, for example, to get the north pole on the right end of the stator expansion and the south pole on the left expansion of the stator here. So you have the possibility to, say, get this configuration for the rotor. Then you move from energizing the phase A, so both left open, and then phase B is energized. V plus put it, say, according to the node B prime and short in B. Current flow in the direction of the yellow arrow, and then you have north pole and south pole in the stator expansion as indicated here, and this provides 90-degree rotation clockwise of the rotor, etc., etc. So you alternate excitation in the phase A and B, etc., in the same way I show you. This is exactly the behavior I described you before. But from now on, let's just focus on the unipolar motors. Now you have the same configuration, so 2 phases, A and B, 4 expansions in the stator, rotor, which is permanent magnet configuration, cylindrical shaped, north and south, 2 poles here. Now the winding have these common terminals, okay? You can see this terminal here. So you have the 2 hands and a third terminal, which is in between. The node in between is always connected to a positive battery, positive, say, continuous voltage. And let's start, for example, with this configuration and put in the phase A, the winding A, V plus and short on the right here. A current flow in this, say, half of this winding. The phase B is not energized at all, no current flowing here, so both left open, the terminals. The current flowing in the right half side of this winding excite north pole configuration in the right and south pole in the left stator expansion provides a 90-degree, say, rotation. Then you left open winding A, you have to energize phase B. For example, you can energize by putting V plus and then common node and shorting the node, say the bottom node here. Okay, the current flow in the half of the winding B with the direction that you can see in the green arrow, and these excite, for example, this configuration for the expansion of the stator in the phase B, making possible a clockwise rotation, 90-degree alpha step of the rotor. Then you need to energize another time phase A and not more phase B, but now the situation is reversed with respect to the number 2 step, in which I have now opened the right-hand terminals of the winding A, but you have to short the left-hand terminal of the winding A. So the current now flow from the center to the left terminal, okay? This situation is not the same you can see here. But this situation is required to, say, reverse the configuration of the north and south pole with respect to this one, making possible another, say, 90-degree clockwise rotation of the rotor. The energized phase A and energized phase B, but with a different configuration with respect to the step number 3. Okay, now the current flow from the, say, the top side of this winding, this configuration, the winding B, because we have V plus in the center tap, and then you have short in the highest terminal node. And this brings to this specific configuration north and south pole, which is the opposite you can have in the phase 3. Okay, so even that configuration, by using just, say, unipolar current in just half of the winding, you have these the same behavior as you can have for the bipolar stepper motor. The driving here is a little bit more simple that you can have for bidirectional driver you need for the bipolar motors, okay? Let me just to share the whiteboard to discuss in a circular way what happens for unipolar motor in the configuration I showed you before. So 2 phases. So let me schematize. Okay, you have A and A prime. You have the rotor, which you have north and south pole. Something like this. And then you have B and B prime. Okay, this is the situation I depicted before. So I have a voltage source that I call V. This voltage source is provided to the phase A and is provided to the, say, center terminal of the phase A. So the phase A has 2 windings here. This is the node A and this is the node A prime, okay? This is the center terminal. Let me call this, I don't know, C. C here. And then you have 2 switches connected to the reference node. This is the phase A. And then you have the phase B, in which V is connected to the central terminal. So this is CA, and this is also CB. And then you have 2 other switches. This is B, and this is B prime. Okay, and this is the phase B. Okay, so this is exactly the same description as before for two phases case. Okay, so what happens at the beginning? I have to excite the phase A and not the phase B. So I have this situation. The switch A is closed. A prime is open. The phase B is not energized at all. This is what in the previous figure was indicated as the step number 1. Okay, then I have to energize phase A to energize phase B, and so the next step is to have the same circuit. No current flow to the phase A. Now the current flow to the phase B. A prime are left open, B is connected to ground, B prime is open. Okay, so in the first case, the current flows interiorly here. Now the current flow here. This is the step number 2 in my previous discussion. Okay, then I have to energize again phase A, but now the situation is that I have to connect A prime. A left open, A prime connected to ground, B is not energized. So the current flows here. And this is step number 3. And then finally, I have the step number 4, in which I have to energize phase B, but specifically I have to connect to ground B prime. All other windings are left open. A prime and B. This is step number 4. The current flows in this way. Okay, so as you can see, the current is always unipolar, so always they flow in the same direction, but in each time in a phase and in say half of each phases, which is different. Now look at this kind of behavior, and specifically this is a switch. Okay, so these are switches, and the switches can be commanded, for example, by a signal. Okay, so you can have a control signal which is applied to each of these switch in order to define the status of the switch. Okay, so for example, for a MOSFET transistor, the voltage you apply between the gate and source terminals of the MOSFET trigger the behavior of the MOSFET at the output port, which is composed by the terminals between the drain and the source. Okay, for example, if the voltage VGS is less than, say, the threshold of the MOSFET is open. So at the output port, drain source, this MOSFET is, say, like an open circuit. If you drive the MOSFET with a voltage VGS which is higher than the threshold, and you drive this MOSFET in the, say, resistive linear operating region, you can consider this MOSFET fully conducting. So you can see that this MOSFET basically is a very small resistance between the drain and the source. You have almost a short behavior, like a closed switch. Okay, so which is the, say, behavior of this signal, common signal for this MOSFET, or for this, say, generic transistor that you can employ as switches. Let's start from our signal. Remember what I said at the very beginning of the discussion of the stepper motor, that at basic, say, input signals you can have in stepper motors is a train pulses. You have, say, sequence of pulses, and for each of these pulses you can have an alpha p rotation at the motor shaft. I remember that this signal, I call this signal as I in my, say, in the slide you can see. This quantity here is periodic, so you have a period here. So for example, let me just consider the first step. Suppose that the first step is associated with the first rotation, and so with the step number 1. So when I energize phase A prime, so that means that my, say, node A should be, say, connected to ground, and so this means that I have to close the switch A. So this is the signal, the common signal for the switch A. Okay, this means that let me put a name for each of the switch. Let me that this is SA, SB, SA prime, sorry, SB, and this is the switch B prime. Okay, so this means that here SA is on, here SA is off. So when this common signal is, let's say, I, logic level I, the switch is on. When the common signal is low, the switch is closed. Okay, so in the first step, which is the step number 1, I have that. So this happens for the first pulses you have at the output. The switch is on, so the phase A is energized, so you have this, say, alpha p rotation. Which is the next step? The next step is the step number 2, in which you have that the switch SB is on. Okay, so you have to provide a command to this switch to make the switch to be fully conducting. Okay, so at this second pulses is the switch SB, which is closed. So this is switch B. Also SB on, SB is off, and SB is off when the common signal is less than the threshold. Let me put here 0 or 1. So this is the step number 2, which is now the step that you have to consider, is the step in which the phase A is again energized, but now is the A prime, which is energized. Okay, so this means that you have to, for this first third pulses at the input, you have to energize this phase as A prime on. Okay, so we are here as A prime on, as A prime off when the signal is, say, null. And then at the end you have this final step This is step number 3. And this happens for the 4 pulses, and which you have B prime on. So this is the phase number 4, etc., etc. Okay, so these are the, say, command signal, command logical signal for SA, SA prime, SB, and SB prime. When the command signal is 1, the switch is fully conducting. When the command signal is 0, the switch is, say, fully open. Okay? And so there is this correspondence with the input pulses you provided. Okay? Of course, this sequence is for clockwise rotation. Remember that if you, let's say, change the sequence that I have here, you can have, say, anti-clockwise rotation. Okay? This depends from another logical signal, which is the signal R, provided the input, which is, can be 0 or 1, depending if you want clockwise or anti-clockwise rotation of the motor shaft. Okay, but anyway, this is what the sequence of the logical signals you have. Okay, so this means that if you look at this, say, operation, you can see that I need a signal I, which is the train of pulses here, and a logical signal R, clockwise or anti-clockwise, the direction, that are generated by, say, signal generator, oscillators, etc. So, but these pulses need to be modified in order to generate the sequence of command logical signals I showed you before. So from this configuration, you have to, say, split into different signal commands. This is made by a circuit which is called the sequencer. Okay, you have here a number of phases. N is the number of phases. In our previous example, just N is 2, okay, because we have A and B. And for each of these number, you have a signal which is, so N command signal, like this one, okay? So SA, SB, etc. So this is the set of command signals that are provided to the driver. Okay, and the driver is eventually connected to the phases of the motor. Okay, so for example, you have the phase A, so we have a current IA, this is the phase B, etc., etc. So the driver is the specific circuit. Up to now, let's say, up to this point here, we have just logic signal. Logic signal means low power signal. Okay, but the driver, let's say, amplify the power of this command signal in order to generate the required current to get the required torque. So this is the, let's say, a power circuit that translate command into, say, current flowing into the phases. Okay. This is generic description of, say, the block diagram needed for, let's say, my stepper motor. Typically, these two blocks here, the logical part, can be generated by specific integrated circuits, okay, that can have on the same semiconductor substrate the oscillators needed to generate this, say, signal here, okay, and the sequencer that generate the specific logical commands for the driver. Okay, the driver typically is something which is not included in this part. Sometimes for low power situation that you can have also the driver included in, let's say, in the integrated circuits, and then you have just to connect the phases, the windings of your stepper motors. Okay, here you have the stepper motors winding. Let's have a look at these, the behavior of the current flow into the phases. Okay, when you have the phases that are excited, so when the corresponding switch is closed, a current flow to this phase. Okay, which is the behavior of this current, because this is very important, and the behavior of the current is the characteristic that changes depending on the driver you are using. Okay, so different driver leads to different behavior of the current flow into the phases with the same command signal at their inputs. So let me just to discuss this topic. Suppose that this is the logic command, and the logic command is something which is described by a square or rectangular waveform. For example, SA, SA prime, SB, etc. Okay, so it means that here the switch is on, here the switch is off. Okay, exactly the same behavior I described it before, which is the phase current behavior. The phase current will depend on the driver circuit, okay, because it's the driver that translates this command into a, say, power current flow into the phases required for obtaining the torque I need. I just, at this phase, at this stage of my explanation, I just see that what is the ideal current I want to get. The ideal current is something that has a behavior which is very fast responding to the command. Okay, it reaches a value specific for my application that immediately goes to 0 when the switch will be left open. Okay, here the switch is closed, so a current flows. Here the switch is open, so no current flows. So my ideal situation is that in which the driver is able to generate in a very steep fashion the current I need. It reaches a value, and then when the logical command they drive the switch to be open, the current goes immediately to 0. This current is, let's say, called this current I-on, for example, the current flowing to the phase when the phase is activated, is energized. The value of this current depends on, let's say, the manufacturers. Typically, it can be range from, say, different level. Okay, so let's say that can be no less than a minimum value and no higher than a maximum value. Okay, not lower than a minimum value, because I want to obtain specific level of current to, say, generate the magnetic field which is, say, needed to make possible a rotation, so to generate the torque I need. Okay, for example, current that are very low cannot excite enough magnetic field from the stator to make the rotor to, say, moving, and no more than a maximum value before you can have some, say, overheating problem. Okay, the winding, remember, is something which is not ideal. You have resistance, loss resistance of the wire, of the copper, of this winding, and so you have too much current flow into this wire. You can have, say, excessive power dissipation. Sometimes this can be done, can be, say, some harmful to your application. Okay, the current can be ranged from a specific level. Okay, but what is ideal here is that you have a very steep fashion in the turn on and turn off of the phase. Okay, this is called the turn on of the phase, and this is the turn off of the phase. Of course, this situation is ideal because suppose that I want to say accelerate my stepper mode. So what does it mean, accelerate stepper mode? It means that my pulse per second provided at the input, so this frequency here, is increased. What happens if I increase the frequency? If I increase the frequency here, it means that these pulses, let's say, are, let's say, closer each to the other. Okay, the period, it becomes very small and the frequency goes high. So it means that these pulses, the pulses of the command signal, reduces, okay, become narrow, and the current so becomes very, very, very narrow. Okay, but for higher pulse per second, okay, provided at the input, this pulse becomes very narrow, like for example here. Okay, so this is the on phases. So on duration becomes narrow, but say since you have these turn on and turn off that are very steep in fashion, nothing changes, nothing happens. This is possible. So you can increase power, pulse per second up to very incredible value, and you can get the same torque. So this situation leads to a graph, which is the torque generated by the motor versus the pulse per second, which is, let's say, more or less constant. No problem. If you increase the step, the pulses, the frequency of the input pulses, since you have this behavior, there is no problem. You can get the same torque at any frequency of the input pulses. Of course, this is just an ideal situation, because if you have a more realistic phase current provided by, say, practical driver connected to the command signal, something like this. Okay, so instead of having, let me just put here the ideal situation, this behavior, here, ideal, you have this red real behavior. Okay, you have something that is not immediate in, say, going into the nominal input current. Okay, it takes sometimes at the turn on and at the turn off. So what happens when you increase the pulse per second? What happens is that in specific situation, for example, let me just indicate here, as you can see, this is a graph. When you have another step here, the phase A is again to be on. But if you increase the frequency, it happens at a certain point that these two pulses for the phase A are very close each to the other. So it can happen that you have a situation like this one. And then you have to increase. So as you can see, these pulses are so close each to the other, then, for example, the current never reaches zero. And if the current never reaches zero, means that you have the phase always energized, the phase A, for example, okay, even when the phase B is energized. So there is no more the situation which you have just one phase on. You have phase B is energized, but then you have a current circulating the phase A. So this is a problem for, say, your correct position. Remember that one of the main features of stepper motor is that you can have a direct relationship between the pulses that you provide the input and the position of the shaft. And if you increase even more the frequency, you can see a situation like this one. The current goes up, but then immediately goes down, and then goes up, goes down, goes up, etc., because the steps are, say, very close each to the other. And this means that, for example, my ion minimum is here, but this current never reaches the minimum current, because before reaching the minimum current needed for getting that specific torque, another pulse comes in order to have another pulse here. So in that situation, of course, leads to the reduction of the torque. Of the variable torque. And so a more realistic graph of my torque versus the pulse per second is that if the pulse per second is, say, quite low, you can have the maximum possible available torque. And then increasing the pulse per second, the torque goes down. Okay, so it's no more ideal like before, but is something like this. So that means that depending on the driver, you just can employ your stepper motor for very low range of the pulse per second at the input side. Okay, so all the effort in building the driver for these applications is to generate a current in the phases according to the command signal provided at the input here. Okay, according to this set of input signal, to generate a current that has a very fast turn on and a very fast turn off. Okay, so this is my goal, in order to increase a little bit this curve, let's say something like this, which is better, so that you have a wide range of frequency that I can employ. Okay, so let's start discussing the driver. So let's now focus on, say, the electronics. So let's focus on what's inside this block here, step by step, in order to see what are the solutions that are invented in order to have the current faster at the turn on and at the turn off. Okay, so the first driver that I want to describe is what is called the L over R driver. Sometimes this is also called constant voltage driver. Okay, let me just focus on one phase. Okay, I said before, and this is indicated here, okay, that for each phases I have just, say, these branches in parallel. Okay, each branches is composed by my winding and then a switch. Okay, so just focus since they are the same on one of this branch, okay? Then you have to have multiple branch, you have to make it in parallel, but this is not a problem, okay? So, which is the basic implementation? Exactly the implementation I show you as a generic principle of operation, okay? Supply voltage, the winding, and a switch. So this is the basic idea. So suppose that I have here the voltage V. I have my winding, and let's suppose that my winding is for the phase A. So let me call this LA. And the winding is described by, say, the model, which is composed by the inductance of the winding, LA, and the losses of the winding, RA. These are two parameters that are indicated in the datasheet of the stepper motor, okay? And let's suppose here you have a switch that, for example, is an N-channel power MOSFET, okay? And here we have the input. Reference signal is here. The current flowing here is the current flowing through the phase IA. So what happens? When the switch is commanded to be closed, so when the voltage here is at a high logic level, so higher than the threshold of the MOSFET, we can suppose that the MOSFET is, say, closed. And also by taking, say, some approximation, we can say that, suppose that between the drain and the source, we have a real short circuit. You know that there is not completely true. Here you have a resistance, which is, say, the Aron resistance, but just for, say, illustrating the behavior, consider that the MOSFET as a closed switch is a perfect short, okay? So RA, LA, RA, this is the current IA. So let me say that I can describe this behavior by putting, say, some, say, first order linear differential equation like this one. The voltage V is the summation of the voltage that you have across this inductance, which is LA DIA over the T plus the voltage drop across this resistance, which is RA multiplied IA. And some simple manipulation, the I on the T plus RA over LA IA is V over LA. Okay, the standard conventional expression of a first order linear differential equation, which is the, let's say, initial condition. The initial condition is that at the time instant which I have, say, the switch on, the current is the current flowing to an inductor should be the same of the current flowing an epsilon time instant before the switching action, okay? And this is 0. Before the turning on, the switch is open, okay? And so when the switch is open, the current flowing to the inductor is null. When you close the switch, the current at the beginning is null because it's the current flowing to an inductor. So the inductor tries whatever it takes in order to have this current to be constant, to be 0. Okay, so you can solve this equation, which is a first order linear differential equation, in a very simple way. When you have just a circuit which you have just one time constant, it's simply to see that you can find the solution by applying these simplified expression. Okay, that says that solution of a first order linear differential equation, which you have just one time constant, is that you have the current, in that case, flowing at time t infinite, minus the difference between the infinite current minus the current flowing at time instant 0 plus, exponential to the minus t over tau. Okay, tau is the time constant, and this is, let's say, easy to understand that is LA over RA. IA at infinite time is the current that flows when you wait for t infinite. And so when you wait for t infinite, this is V over RA. And the current at 0 plus is no more than this one, so it is 0. So my solution is that the current IA is something like V over RA 1 minus E t over tau. This is the solution. Okay, whatever is the method you apply, this is not, say, something which is new. So what happens at the two nodes? Let me just put on a graph, which is the behavior of this current. The current was 0 before the time instant 0, then the current goes, let me put here V over RA, which is IA at infinite. Let me call this, say, IA, which is the static current flowing to the phase. And said you have this one current. So you have something like this. As you can see here, there is a certain time interval that is needed for the current to move from 0 to the static value, which is the value of the current when the phase is on. Okay, IA is the capital letter, is the current that you can have when the phase is fully energized. How can we measure the rapidity of this current in reaching the static stationary value? Typically, this is done by looking at the slope at the origin. Okay, so the slope at the origin means the I A over the T at t equal to 0. Okay, this is simply given by this equation here. For evaluating this expression for t equal to 0 brings that this part here is null, because IA, the current at time instant equal to 0, is null. So this is only V over LA. So the slope here at the origin depends on the supply voltage you have at the input and on LA. Of course, LA is something that you cannot choose. Okay, it's something that you can have when you select your stepper motor, providing you the correct torque for your application. Okay, so it's something that you cannot change. The only way to improve, to make faster this transition, is to increase the voltage V. Okay, so you can have faster, say, slope here, for example here, so reaching my steady state value faster when you have larger V. But what happens if you increase the voltage V supplying your phase? Then also the current here is increasing. So the current goes here. So you have something like this, if you want. Faster transition, but also higher current. Okay? This is for V prime higher than V. But remember what I said before, it's not, let's say, allowed for the current flow into the phase to overcome specific maximum value in order not to destroy your phase, okay? Because the power dissipated is too high, that, say, the temperature is large. And so this is a problem. Okay, so you cannot act in too much on this kind of rapidity of this current. Okay, the current is, let's say, as this slope here, and you have no more action to increase this variation. Okay, so summarizing, in order to have faster transitions at turn on, V should be increased, but this is limited by IA maximum value. Okay, so you have this variation, you don't know how to increase this, but see what happens at the turn off. At turn off, you have your switch that is completely conducting, and then you instantaneously command the switch to become an open circuit. Okay, so let me just see what happens. This is what happens an instant of time before the turn off. I have IA, capital letter, which is the static equation, static current, which is V over RA. Okay, this is the current flow into these circuits. The switch is closed, and then suddenly I make the switch open. Okay, suddenly, so the current suddenly from IA must go to 0. But here you have an inductance, and the inductance try to perform all the efforts it can done in order to maintain the same current level that you have before opening your switch. And in order to do this, what happens is that the voltage across the inductance change its polarity. Okay, here the current should go, say, negative. Okay, so the I on the T should becomes negative. Okay, so because it must, let's say, reduce the value. So the I on the T is negative. And so you think this equation for VL, it means that VL becomes, say, negative. So the voltage across the switch here, the phase, can become at this point at a value which is less than 0 volt. So the voltage that you can have here in order to maintain the current at the same level. So remember that here you have a MOSFET, okay? But the MOSFET always have what is called the body diode across it, okay, between the drain and the source. So when it happens, when the voltage here at the drain reaches a value which is less than this value that you can have at the source, then this diode, the body diode, is conducting. So here you have the body diode conducting. So the current IA forces the conduction of these diodes. So the current flow is here. The MOSFET is off. Okay, the MOSFET is open, but there is the body diode. Okay, so the current flow is in this situation. What happens that in that situation? That the current is flowing in this case, but see what happens that the current flows from, let's say, the cathode to the anode, and so you are in a situation that in a very fast, say, way leads to the breakdown of the MOSFET. The MOSFET is operated in this region here. The MOSFET is in cutoff, so the current ID is null. The voltage VDS here, say, can become larger at a certain point that reaches the breakdown voltage. Remember that we can call this as breakdown voltage between the drain and the source. And when it happens, the current flowing in these diodes, say, make these devices to be, say, completely destroyed, because there is a very large value of current flowing here, and there is a voltage across the MOSFET. And so in that situation, the power dissipated during the breakdown situation, the breakdown operation, is so high that the MOSFET is no more working as intended. Okay, permanent failures due to this behavior. Okay, so what happens here that you open your switch because you want to turn off the phase, the MOSFET, say, blow up. So this is not exactly true, because of course operating a MOSFET exactly at the breakdown voltage is something which is not, say, something which is not permitted. Okay, so is always you have to operate your MOSFET for a voltage V which is less than the breakdown voltage. This is for sure. This is a region in which you cannot operate safely, because if you go there when the voltage is exactly the breakdown voltage, it happens that, say, the energy dissipated is so high. But anyway, the mechanism by which this MOSFET destroys itself when you operate the MOSFET at the breakdown voltage is something which is related to the, say, a thermal process that is involved inside the semiconductor material of the MOSFET. And this involves also the thermal capacity of your devices. It happens that if you are able to operate the MOSFET in the breakdown voltage without, let's say, involving too much energy, that situation can be, let's say, affordable. So you can stay in the breakdown voltage when the energy involved in this action is not so high. Because if the energy is not so high, the semiconductor material has not the time to increase the temperature over the maximum temperature which is admissible for that specific semiconductor, which is about 150 degrees, 170 degrees. What that means that if you go in the breakdown voltage, but you stay there for a very limited interval of time, and then you go, say, below breakdown voltage, this situation can be, let's say, sometimes can be evaluated to be, say, supported by your MOSFET. Okay, depends on the MOSFET you are using, depends on the MOSFET at what is called avalanche capability, you can find in the datasheet, okay? But if your MOSFET is a kind of MOSFET that can support avalanche for a limited amount of energy, then operating exactly at the breakdown voltage is possible. This depends on the amount of energy that we call avalanche energy involved. Okay, so summarizing what we said up to now. If you want to turn on your phase by these L over R circuits, there is no, say, measure you can apply in order to make faster transition, because it depends on the voltage V. If you increase the voltage V, you can have higher on current, possibly destroying your phase. At the turn off, the situation could be even worse, because when you command your switch to be open, okay, the current in the inductor, which say want to remain always the same, induces conduction in the body diodes up to the breakdown voltage of the MOSFET. In that situation, if you don't have MOSFET with avalanche capability, the MOSFET say blow up. But if you are able to say maintain the energy involved in the operation exactly at the breakdown voltage, the situation can be reversed. So the situation does not lead to permanent failures. Okay, when you decrease the voltage, the MOSFET operates as intended. So the next step, and we will do this next week, is to compute the amount of energy of this transition and to understand which are the parameters that we can play on in order to reduce the amount of energy and to use this MOSFET exactly in this way in the breakdown operating region for the turn off. Okay? Have you questions, problems, doubts? Whatever? No problems? No problem, no doubts? Okay, so see you next Tuesday at 10. I wish you a nice weekend, and thank you all. Bye.